Okay, this is exciting. We're going to learn the fundamental theorems of calculus. So I'm going to go through this first part fairly quickly, the assumption being that you've already read through this and you've already tried to answer these questions on your own. The idea is that if you and another person have the same velocity function, then even if you're starting in different places, your velocity graphs are going to look the same. So in this particular case, you're going 60 miles an hour at a constant rate, and so is your friend. So both of your velocity functions are just this horizontal line here. But if you are starting at mile marker 0 and your friend is starting at mile marker 20, then your position graphs won't be exactly the same, right? It won't be exactly the same because OneNote is going to annoy me here. Because you're starting here at time t equals 0, and your friend is starting here at time t equals 0. Now, if your velocities are both 60 miles an hour, then 1 hour later, you're 60 miles down the road. And then 2 hours later, you're 60 more miles down the road. And you would have a position graph that looks something like this. Whereas your friend's position graph, she would maintain that 20-mile lead on you. So we'd have a parallel line. Same slope, right? Slope of 60. Because the derivative of position is velocity and you have the same velocity. So the change in your position is 120 minus 0, which is 120 miles. The change in your friend's position is 140 minus 20, which is also 120 miles. We're both moving down the road for 2 hours at 60 miles an hour, so we're both going to travel 120 miles, even though those exact positions don't line up, right? We don't end up in the same place because we didn't start off in the same place. So another scenario might be if the velocity is decreasing at a constant rate. So this is not a constant velocity, but a constant acceleration, right? We lost 60 miles an hour over the course of 2 hours. So that would be negative 30 miles per hour squared might be our acceleration, right? Negative 60 miles per hour divided by 2 hours is going to be negative 30 miles per hour squared. Okay, and just as before, we're going to assume that you start at mile marker 0 and your friend has that 20-mile lead. And same as before, you're going to see that your friend is going to maintain that 20-mile lead on you. Your position function is going to be, well, let's see, what is the acceleration? The acceleration is equal to negative 30, so your velocity is going to be negative 30t. Plus the initial velocity of 60 miles per hour. So that means that your position function is going to be negative 15t squared plus 60t plus 0. Right? Take the antiderivative of the velocity function and you get your position function. And it's a plus 0 because your initial position is 0. And your friend's position function, well, that's going to be the same thing, except she has that 20-mile lead. So that plus 20, that constant of integration is going to be plus 20. So when you sketch those, you're going to get these parabolic graphs. Let's see. So at t equals 0, you'll be at 0. At t equals 1, you'll be at 60 minus 15, or 45. And then at t equals 2, let's see, so that's going to be negative 60, that'll be 60, right? So I believe that's going to be the vertex of your parabola. You could verify that by looking at the velocity function and realizing that that's where we hit a velocity of 0, so our slope of our position function will equal 0. And your friend, again, is going to do the same deal, but is going to be shifted up 20 miles. Okay, your change in position is 60 minus 0, or 60 miles. and your friend's change in position is 80 minus 20, or 60 miles. And again, it's not at all surprising that your change in position and her change in position are the same because your velocities are the same at all points in time. So now we want to try to find that connection. What is the connection between the velocity graph and the change in position? Well, some of you might already know this, that when we look at this rectangle here, this rectangle has a height of 60 and a width of 2, right? A height of 60 miles and a width of 2 hours, and miles per hour, excuse me. So when you multiply these together, you're going to get that 120, right? So you take the y value times the x value. What you're really doing is you're finding the area under the curve. And that's a nice connection to what we've just been doing, right? We've been approximating and actually using limits to find exact areas under the curve. And now we're actually seeing that the area under the curve is actually equal to the change in the antiderivative, right? So the position function is the antiderivative of the velocity. So when we found that delta x, that 120, we did final position minus initial position after we took the antiderivative of the velocity. And take a look, same thing's true here. We have, this time the base is still 2 hours, and the height is still 60 miles per hour, but it's no longer a rectangle, it's a triangle, so it's going to be 1/2 base times height, and that 60 comes into play. So this is actually pretty monumental, because what we're discovering is that the area under the curve, which we've already talked about, is going to be denoted as this definite integral from a to b of some function. Well, what we just found is that we would take whatever that function is and integrate it. We take the antiderivative of it to figure out, in this case, velocity went to position, so that we could find that change in position. Okay, so what that means is we're going to figure out what the antiderivative of f is. I'll call it g, evaluated at b and a, and then we subtract the two. So we're going to do g of b minus g of a, where g is the antiderivative of f, or where f is the derivative of g. And that's actually the fundamental theorem of calculus. And this is a really slick, quick way of calculating the area under a curve without having to deal with all those rectangles or trapezoids or using limits of sums. It's a much, much faster way of finding this problem. Now, one thing I want to finish off this video with is to try to make that connection between area, which is using the antiderivative, and the slope, which is using the derivative. It's not at all obvious at first glance that the derivative and the integral should have to do with slopes and areas, respectively. But if you think about the operations, right? If you think about the fact that when you're finding the slope is the change in y divided by the change in x. Well, the area is actually the change in y times the change in x. And that division versus multiplication, well, those are inverses of each other. Derivatives and integrals are also inverses of one another. So if you think about it as a reversing process, which is exactly what integration is, then hopefully that makes a little bit of sense, and we can kind of start making those connections between derivatives and integrals and their applications.